First problem that we're looking at here reads that the distance a car travels from when the brakes are applied to the car's complete stop is the stopping distance. This includes time for the driver to react. The faster a car is traveling, the longer the stopping distance. The stopping distance is a function of the speed of the car. A little bit later on, we're going to define what that means. Right now, we're just going to analyze that situation and look at the graph. So the first question that you saw asked, why do you think this graph is a curved line rather than a straight line? I'm really interested to see what you guys have to say there, so I'm not going to write my answer in here, but as you're working in Pear Deck, make sure that you're paying attention for my comments that are coming through to you individually. What do you think is going on here? Why is this a curved line comparing speed to stopping distance rather than a straight through diagonal? Question number 2 says represent the relation above using a mapping of the domain and range. So we talked about mappings whenever we were talking about relations. Remember that a relation is just a set of coordinate points comparing two variables. So I'm comparing speed to stopping distance here. I want to create a mapping of the domain and the range. Remember here that domain is your set of x values, range is your set of y values. So my mapping, I'm going to compare my domain and my range, and then we draw them in our mapping symbols. Remember, our 2 rules for creating a mapping is to not repeat any values when we're writing them in and to order them from lowest to highest. So if I'm talking about the domain of my function, I'm going to go ahead here and I'm going to pull out my x values. So technically, I would have every single value here coming through the line. I'm, however, only going to pick these points just to show as a reminder what our actual mapping diagram is going to look like. So keep in mind that your speed is every single point on this line. In my diagram, though, I'm only going to pick out those points that we can actually see. So going from lowest to highest, I'll start down at 0. And then my next x value that is plotted is a 20. And then it looks like I have 30, 40, 50, 60. I'm running out of space here. Again, that's not all of the x values in the function because my line is going through, so I'm reaching all of these speeds, but just for the sake of reviewing what my mapping diagram is, I'm only pulling out those coordinate points. So then I'm going to go ahead and list my range. So what are my set of y values? So now I'm just going to go ahead and read my graph on the y-axis. I'm going to start down here at 0, and then I have about 50, and we're going to do some estimating here. Then it looks like I'm halfway between 50 and 100, so let's estimate maybe about 75. And then it looks like I'm a little bit above 100, so maybe let's estimate 120. And then I look like I'm right between 150 and 200, so let's guess 175. And then I'm right underneath 250, so let's guess 240. And then my last coordinate point that I can see looks to be about 310. So that's my set of y values. So then the mapping diagram says, go ahead and match up all of your x and y coordinates. So in this case, I have 20 going to 50. So when I'm going 30 miles per hour, I am 75 feet away. 40 miles per hour, I'm 120. 50 miles per hour, 60. And here you go. So there's your mapping diagram. Again, a different way to represent the graph. It's showing you all of your x values or your inputs, and then all of your y values, and you're mapping them to each other. So whenever we start discussing functions in the next video you're going to look at, our definition is going to change what we think about graphs, and we're really going to hone in on this idea of a mapping diagram and seeing the arrows map one coordinate to the other.